Welcome back to another video. In this video, we'll be talking about covalent bonding, which is the final type of bonding, or the final type of bonding, that main type of final bonding that we'll be talking about in chemistry. So let's proceed with what we're going to learn in this video. So the learning outcomes from this video will be you will understand what a covalent bond is, how to distinguishingly find out that a particular compound has covalent bonding, and you will find out the properties of covalent bonds. So there are different types of covalent bonds. There are covalent bonds in atoms, in compounds. There are so many things. So you will find out all of the properties that you need, and also we will talk about the giant covalent structures, which is another extension that we would see in covalent compounds. Okay, so what is a covalent bond? So a covalent bond is simply a bond that happens between non-metals and non-metals. Okay, so in the previous videos we did about ionic bonding. So ionic bonding was between metals and non-metals, where you saw a exchange of electrons, where the metals gave away its outer shell electrons and the non-metals accepted the outer shell, the electrons given by the metal to their outer shell. All right. Now here in a covalent bond, it takes place between non-metals and non-metals, and here we don't see any exchange of of the valence electrons, but we see that the valence electrons are shared. There is a sharing of valence electrons in order to obtain the stable electronic configuration. Okay, and the other important thing here is now in ionic bonding we did not see double bonds, triple bonds. In here you will see double bonds and triple bonds also. And we'll look into, there are many examples that I have also in the upcoming slides. We'll look into all of that. And the other important thing is, now in covalent bonds, they form bonds with multiple elements. Okay. For example, there are different examples, right? Many organic compounds have different elements being covalently bonded and formed a particular compound. Okay. And the other thing is, there are molecular and macro compounds. So molecular means small compounds, macro means considerably large amount of structures, which we refer as giant covalent structures. Okay, and very important thing is that remember that hydrogen also forms covalent bonds. I know hydrogen, if you see in the periodic table, you will see hydrogen in the group 1, that is where it is placed. So you might think it acts as a metal and then it gives away its electron, but it's not it has no ability to give away his electron, because if he gives away his only electron that he has, that means he's nowhere there. So the only thing he can do is he can share that outer electron with some other element, a non-metal, and then form a covalent bond if he wants to react. All right. Okay, so first we'll look at bond in atoms. Okay, so we'll look at the bonds in atoms. So for example, there are certain elements in the periodic table which we refer as diatomic molecules. Okay, so for example, if you remember, now there are certain elements like chlorine, fluorine, all the group 7 elements, then oxygen, nitrogen, hydrogen, all of these we would always, if we write chemical reactions, we don't just put H, or we just don't put O for oxygen. We always put O2. This is because they are diatomic molecules. So how do they achieve this diatomic thing? What they do is they are covalently bonded to each other. So for example, if I have the example of chlorine, okay. Now see chlorine, this chlorine has 7 atoms in its outer shell. Why does it have 7 electrons in its outer shell? Because it's in group 7, right? We know that. It should not be a big issue right now. So there are 2 chlorine atoms which have 7 electrons in the outer shell. And when you have 7, that means it's unstable, because we know this for an atom to be stable, it needs to have 8 outer shell electrons. So what does he do? Now these both guys are non-metals, so none of the guys can give away electrons. Okay, they can only accept, but no one is giving. So what they can do is they can share the outer shell electrons. So they bond in a way, you can see here, where they bond with each other. So what happens when they bond with each other? If you count right now, how many, after this bonding happens, how many outer shell electrons that each of the chlorine atom have? They have 8. You can see here 2, 4, 6, and 8. So similarly, if you look at the left hand side chlorine atom also, it has 2, 4, 6, and 8. Okay, so simple as that. Okay, so what they do is they will share the outer shell electrons in order to achieve stability. So for you to check whether you have correctly drawn the covalent bonding, what you can always do, you can count the outer shell electrons and see how many are there. If you count them and you see that there are 8, that means you have correctly drawn the covalent bonding. If there are more than 8, that means you have done some mistake there. Or if there are less, you have also done a mistake. So hydrogen, if you see hydrogen, the second example, hydrogen. So hydrogen has 1 electron in its outer shell. So similar should be for another hydrogen atom. It also has 1. So they covalently bond and they form same with 2. So we know that 2 is also if you achieve 2, that means you are achieving stability, right? So yeah, that's one thing. So this is the way they share. See, they're sharing. Okay, this is what we call the sharing of electrons. So this we can see here. Now in both of these cases, both of these examples, we can see that always one electron from each atom is only being shared. All right. So here this electron, if I can use the annotation for a moment, yeah, I can. So you can see this electron and this electron is the one that is being shared. So this guy gives this electron, this guy gives this electron, and this is the one that is being shared. All right. So 1 electron from each atom. Here also what has happened? 1 electron from each atom. From this hydrogen, he gives this electron. From this hydrogen, he gives this electron. And as a result, they are sharing like this. But there are certain atoms that do not, constrain themselves to 1. They have to give 2 or 3 in order to achieve stability. It depends. So if we go to the next slide. Next slide. Here we go. Now here we have oxygen and nitrogen in this slide. So here you will see that difference. Okay. So okay. So oxygen atom, look at this. Now oxygen atom, how many electrons should it have in its outer shell? It should have 6, right? Why? Because it's in group 6. So there are 2 atoms, oxygen atoms like this. And what happens? How are they going to achieve stability? They are going to have to share the outer shell electrons. So how are they going to do it? They will have to, each of the oxygen atom should give 2 electrons. Okay. Why do I say that? Because if they are able to do something like that, only they are able to achieve the stable 8 electron outer shell. So because they gave here 2 each from each of the 2 electrons from each of the atoms, they were able to achieve 1, 2, 3, 4, 5, 6, 7, 8. If you count this side also, you're going to have 1, 2, 3, 4, 5, 6, 7, 8. All right. So which means these shared electrons are common to both of these molecules. So here is an example where 2 electrons are being shared from each of the atoms to obtain stability. Now when we go to nitrogen, it becomes even much more interesting because they have 5 electrons in the outer shell. So for them to share, what they do, they share 3 electrons from each of the atoms in order to attain stability. Okay. So here also, if they share 3, if you count here, there are 6 here, and if you count the left side here, there are 2. So here achieves 8. Similarly, here there are 6 here, there are 2 here, so that means on the right side and the left side nitrogen atoms both have a stable configuration of 8 electrons achieved after they have covalently bonded to each other. So if you are not able to, if you're unable to, look at it in this way and see, you should always count the number of uh, electrons and see how, because if you count the outer shell electrons after the covalent bonding happens, it should always have 8. If it does not have 8, then that means you have done some error somewhere. So that's a particular way where you can recheck your answers before you submit your working in any examination. Okay, so that's why, as I said earlier, also all the atoms that we discussed are diatomic molecules. So diatomic molecules will always have covalent bonding. All right. So next, what we have is we will look at covalent compounds, right? So covalent compounds, it should be always a reaction between a non-metal and a non-metal. All right, but there can be plenty. There you can't say okay, there can be it's a reaction between only 2 non-metals. There can be 3 or many and different elements. No problem. Now here, first example is hydrogen and chlorine. Now we know, I said we stated in the first slide itself that hydrogen does undergo covalent bonding. So hydrogen, chlorine is also non-metal. So what happens with so he has 1 electron here. He also has 1 electron. So what do? These two guys will be, this guy will give 1 of his electron, this guy will give 1 of his electron to be shared. So as a result, we are able to give something like this. Now if you look at the chlorine side, he has 2, 4, 6, 8. He is stable. Then on the hydrogen side, how much does he have? He has 2 from this shared pair. So we know even if he have 2 electrons in his outer shell, 2 or 8, that means he has achieved stability. Simple as that. Then this is the second example. Now this is H2O. You can read it and you might be knowing by now H2O means water. So what has happened? Yes, similarly we have had 2 hydrogen molecules. So hydrogen molecules, how many electrons should it have? It should have 1 electron. And oxygen will have 6 electrons in the outer shell. So when they covalently bond, what happens is oxygen, we know he will share 2 electrons. So he will share 2, and hydrogen, each hydrogen atom will share 1 electron in order to form a covalent bond and attain the stability. If you count here also, the oxygen is having 8 electrons in total, and hydrogen has 2 electrons in total, and they have all of them have achieved electronic stability. So here is another example. Okay, this is ammonia. Okay, so if you come across a molecule NH3, that means in simple words it is ammonia. All right, here also you will see same thing has happened. Okay, you can validate to yourself whether and it's good for reference. Okay, so let's move on to the next slide. Next slide, we have ethanol. So this is a much more complex. So you can have, there can be lot of many complex molecules. So this is one of these are all organic compounds, except for this is carbon dioxide. Okay, so carbon dioxide, look at this very, very clearly how it forms the covalent bond. So these are examples. This is ethanol. So ethanol is basically the alcohol. Regular alcohol contains ethanol. Okay, and this is also another organic compound which is called ethene. You will learn this once you are doing organic chemistry. So these are molecules. So see, in all of these examples here, they have shared electrons, and they have shared in a way these electrons in order for them to achieve electronic stability. All right, so nothing confusing, just you have to look at the electrons and see the pattern in which they can share their electrons in order to achieve electronic stability. Now, there are certain properties we said there are certain properties in these, in any chemical compound there are distinguishing unique properties. So these covalent compounds also have properties. For example, they have low melting points, low boiling points. So if you have to validate, if you have to give an example of it, so water has low melting points and low boiling points, because the boiling point of water is 100 degrees Celsius. When we compare with some other chemical compounds which have absurd amount of absurd values for boiling points, uh, water has a regularly similarly very low melting point, low boiling point. All right. And the other thing is it's insoluble in water. So for example, if you take any uh, covalent compound, as we have whatever we discussed in the other previous slides, if you put it in water, you can't dissolve it in water. It's insoluble. It will remain to be as it is. And the other thing is it does not conduct electricity. Why doesn't it conduct electricity? Because there are no free electrons. If you remember, if you need for a compound to conduct electricity, it needs to have free electrons. If it does not have free electrons, it cannot conduct electricity. All right. Next in store, we are going to learn about giant covalent structures. So one of the giant covalent structures are diamond. So diamond, in what we use in jewelry and all of this stuff. So the property is, now this is the structure of diamond. So this is the structure of diamond. You can see that so all these balls that they have given are carbon atoms. So each carbon atom is covalently bonded into 4 other carbon atoms, and there is no carbon atom that is not bonded. So each time they are bonded. So there are no free electrons. So when there are no free electrons, what happens? It cannot conduct electricity. And because they have strong covalent bonds between them, between these carbon atoms, they are very hard. It's very hard to break them. And also because they're very hard and their bond is very, very strong, they result in very high melting points. Okay. And what do we use this diamond for? Diamond is used in drilling and cutting tools. Because of its very hard property and all of that, we are able to use it in drilling and cutting tools. All right. And also, when you polish diamond, when you polish it nicely and everything, you do all of that, you are able to use them in jewelry. So jewelry also we use because they are hard in structure. If they are very weak, then we don't use it, right? So that's that's the way we use diamond in real life, based on their properties. Next in store is the last giant covalent structure, which is graphite. So graphite, these are graphite. So you can see these are also all carbon atoms. These are all carbon atoms. Each carbon atom is covalently bonded to 3 other carbon atoms. So that means we have one unbonded. So it has one bond that is unbonded. So therefore, that means it can move around and conduct electricity. And because now you can see here very clearly, they are arranged in a way like a sheet. They are arranged like in sheets. So these sheets can move or slide across each other. So because they can slide and slide over each other, it has the property of being soft and slippery. Because it can slide over each other, they are soft and slippery. So for example, if you can see in pencils, now pencil lead is actually made out of graphite. So every time you write with the pencil, there is this flakiness that comes out, breaks down like flakes. So that is because of this slippery property. Okay. So the uses of it is, we said, in pencil leads, then as lubricants for engines, locks, and also as for electrodes and connecting brushes in generators. So these are certain uses of graphite. All right, based on their physical properties. So all of these uses and everything are based on these physical properties. So with that, we come to the end of this video. Also in this video, we discussed about covalent bonding. We looked at what covalent bonding is. We looked at covalent bonding in atoms. We looked at covalent bonding in compounds, in molecular compounds. And then we came across a different subtopic, which is gyral and covalent structure, and we saw that the structures are macro in size and their properties also vary with regard to in comparison to the previous molecular compounds that we discussed. So that's it for this video. I'll meet you in another video shortly. Thank you so much.